Okay, so we've started to explore working in Fock space, and we figured out how to write down the completeness relation in Fock space. Another very basic question that we might want to ask is how do you write down a wave function in Fock space? So let's say that psi, okay, let's have a capital psi like this. This is our wave function in Fock space. And the basis for Fock space is made up of the basis of the no particle sector plus the base of the one particle sector plus the base of the two particle sector and so on. So I can add all of these states together to form my wave function. So I might have some number, C naught, times by the vacuum. Then from the one particle Hilbert space, I might have an integral d3k. Then I'll put C subscript 1 for one particle as a function of k with the one particle states. From the two particle piece, I might have an integral d3k1, an integral d3k2, C2 for two particles. I'll have k1 and k2. And then I could have the ket with k1 and k2. Let's write down one more term. I might have something from the three particle Hilbert space. So this would be an integral d3k1, an integral d3k2, an integral d3k3. Then we would have this function of vector k1, vector k2, vector k3, and then the three particle state. And it would just keep going, okay? So this is looking, well, I would say fairly ugly. So we started off with a wave function, which is just a number. Then we've got a function of 3 variables. Then we've got a function of 6 variables. Then we've got a function of 9 variables. In the 4-particle Hilbert space, we would have a function of 12 variables. And it would keep going on and on. That's ugly because it's so complicated. But anyway, let's not give up. Let's just see what it would be like to describe some process. So let's imagine that we've got a photon. So here's our photon. And then at some point, our photon pair produces. So it might produce an electron. So here's an electron going off and a positron. Here's a positron going off. Okay? So there's pair production. Classic process allowed in quantum field theory. And perhaps the electron that was emitted still has a lot of energy. So at some later stage, it emits another photon, okay? So we've got something like this. This really could be a process we want to study. So let's think about how we would do it. Well, if we were using wave functions in this region over here, up to that point, we would want to have a one particle wave function, which would describe the photon. So we would have a function of 3 variables. And then in this region over here, we've got a 2-particle state. So now we would have a wave function which depends on 6 variables. And then in this final region over here, where we've got 3 particles, we would have a wave function that depends on 9 variables. So what's happening in this theory is we're making transitions from wave functions of 3 variables to wave functions of 6 variables to wave functions of 9 variables. This is such an ugly theory that nobody could love this theory. It's just too complicated. You'll never be able to discuss anything with clarity or to do anything that's useful. So the idea of having a wave function in Fock space is too complicated, and we're simply going to abandon it. Instead, now we are going to start defining and working out what we call the occupation number representation. To the occupation number representation. So these are the ideas that we are borrowing from statistical mechanics from the grand canonical ensemble. And it's going to give us a much simpler way to proceed rather than having a wave function in Fock space. Before we do that, though, we're going to need one crutch. Okay, so if you're not English speaking, you might not know what a crutch is. If you hurt your leg, the doctor will give you two metal poles that you put under your armpits, and you can lean on the metal poles instead of leaning on your sore leg, and the crutch helps you to walk. Okay, so you can look up the word. That's what it's called, crutch. It'll help you to walk. Now, we are going to introduce something that is going to help us to think. So it'll be a crutch in our thinking. And we often talk like that in English. We talk about a crutch. So the crutch that we're going to use to help us to think is that we are going to work in a box. What do I mean by that? We are now going to imagine that the universe is not infinite, but it's a box, okay? So the whole universe is contained inside a box. This box is actually a cube, so the height of the universe is going to be L. The width of the universe will also be L, and the depth of the universe will also be L. We are interested in studying free particles inside this box. And I think that you know that the wave function of a free particle is e to the I k dot x. And we can write this as e to the I, the x component of the wave vector, plus times by x, plus the y component ky times by y, plus the z component times by z. And let me just tell you how my axes go. I'm taking this to be z, this to be y, and this to be x. Now, I also need to impose some boundary conditions on my wave function. So this wave function that we're going to be using, this is a state of a definite momentum. And in our Fock space, we have chosen as our basis states that have a definite momentum. You can see here this linear combination. These are all states with a definite momentum. So that's why I'm interested in studying this plane wave, which is a state of a definite momentum. But I'm going to impose some boundary conditions in the box. I'm going to impose periodic boundary conditions. Okay, so what does this mean? For example, the wave function at the front of the box must be equal to the wave function at the back of the box. So the wave function at the front of the box, well, the front of the box is where x is equal to L. So it'll be e to the ikx evaluated when x is equal to L, and any y and any z, any y and z is at the front of the box. And I want this to be equal to the value of the wave function. Oh, these should all be vectors. Let's make those vectors. The value of the wave function located at the back of the box. And the back of the box is x is equal to 0, any y, and any z. Okay, let's just plug values in and see what we get. So on this side, we'll have e to the I, kx, and then for x, I should plug in L plus I, ky, y, plus I, kz, z. And this should be equal to, now for x, I should plug in naught. So I, kx times by naught, well, that's nothing. I've got e to the I, ky, y, and e to the I, kz, z. So if I look at what this is telling me, it's telling me that e to the I, kx times by L is equal to 1. And I know, of course, that 1 is just e to the 2 pi I times by any integer. Let me call this integer nx. So I learn that my boundary condition forces kx times by L to be equal to 2 pi nx. And that means that actually kx is no longer continuous, but it is equal to 2 pi times nx divided by L. So k has become discrete. If I ask that the value of the wave function on the left side of the box equals the value of the wave function on the right side of the box, okay, then that will tell me, so I'm going to now equate left side to right side. So that means x can be whatever it likes, y has to be 0, and z can be whatever it likes, and that should be equal to e to the I k dot x, with x being the same value, whatever it is, y equal to L, and z equal to 0. So I want you to work out what this condition is, exactly like we did above, and you should learn that ky is 2 pi times by some integer ny divided by L. And then finally, one more condition, we can ask that the wave function on the bottom of the box takes the same value as the wave function at the top of the box. So the condition for the wave function at the bottom, that is when we've got any x, any y, and z is equal to 0, the condition that that's equal to the wave function at the top of the box, that means e to the I k dot x at any x, any y, and z is equal to L. So you go ahead, work out what that tells you, doing exactly what we've been doing so far, and you will find that kz must be equal to 2 pi times by some integer nz divided by L. So what has happened? By working in a box, momentum is no longer continuous. Momentum has become discrete. Kx, ky, and kz are now specified by 3 different integers. Now, this is so useful. It's useful if you ever want to do any counting. So if you have to count states, it's easier to count discrete states than it is to count continuous states. One of the reasons why this is so useful for us is that we've always been normalizing things to the Dirac delta distribution. But the Dirac delta distribution is a distribution, not a function. It's hard to work with distributions. But after we've gone into the box, before, if we had delta of k1 minus k2, so this is the Dirac delta, a difficult thing to work with. After we've gone into the box, it becomes the Kronecker delta. And you probably are familiar with the Kronecker delta. It's equal to 1 if k1 is equal to k2, and it's equal to 0 otherwise. This is such a lovely, simple object, much simpler than the Dirac delta. And that's one of the reasons why our life is going to become simpler. And then also, if you had any integrals over d3k, these will now become some sums over the discrete momenta. So our wave functions can now be normalized to 1. They can be made orthogonal to 2 wave functions with different momenta orthogonal to each other. The wave function itself can be normalized to 1. We don't have to normalize the Dirac delta. We've got nice discrete sums instead of continuous integrals. And if we want to do any counting, it's going to be easier to do the counting with the discrete states. So this is why working in a box is going to make life simple for us.